Okay, and then the last thing we have here is Ampere's law and solenoids. Solenoids? Well, we are going to use Ampere's law to figure out what is the magnetic field around, say, a wire. And Ampere's law is actually really kind of tricky to use. The reason we can really easily use it with a wire is just because the geometry is very simple. And this reminds me a lot about Gaussian surfaces. You can choose a lot of different Gaussian surfaces. Same thing here. You can choose a lot of different Ampere's law loops. So let's just get started. Like, this is our wire with a current I going through it. So Ampere's law is this. Now here's what this means. If you have a loop, kind of like a Gaussian surface, going around a certain current, then if you were to take that loop, say we have a loop here, and chop it up into little pieces, those little pieces are representative of the B here, and the actual length of those pieces are the length right there. So this is the length of each piece, and this is the strength of the magnetic field over each of those lengths. Okay, so in our situation, we're looking at exactly just a wire, and we're doing a uniform loop all the way around. And we're chopping up this loop. It actually doesn't matter which way you chop it up, but it's just easier to keep it evenly all the way around the circle. Now, what's nice about this is the strength of the loop is the same everywhere. So what we can do is we can factor out RB. Kind of like if I have 2 times A plus 2 times B, I can take the 2's and put them out front, factor them out. Same thing here. I'm adding up a lot of things, but this B is the same every time, so I can just put it outside. Alright. The next step is we got to realize that if you sum up, that's what that sigma stands for, all the little lengths of this circle, well, you're going to get a full circle. And that circle has another equation. You could just say the circumference is 2 pi r. Okay, it's looking a lot nicer now. And then the last thing here is we're trying to find the magnetic field based on r and I. So we're going to divide by 2 pi r, and we're going to have this all over 2 pi r. Okay, so you might be wondering, what is this mu 0? Mu 0 is a constant. It's 4 pi times 10 to the negative 7th, and you're never going to need to know this, but it's Tesla meters over amps. Yeah, that weird constant is called the permeability of free space, but really just remember this constant so you can use it. And for a straight wire, if you want to find the magnetic field at any point, then this is what you'll use. So let's do an example now. Let's say we have 2 wires with parallel currents. Of 2 amps. And let's say that these wires have a separation of 1 millimeter. Okay, we're going to answer 2 questions. What is the magnetic field on the other wire? So basically, we want to figure out, if we were focusing on wire A, how is that creating a magnetic field at wire B? And then part B is, we're going to ask, what is the magnetic force? Okay. And I guess I shouldn't label them A and B because B could be confused with magnetic force. So let's just say X and Y wires. Alright, so for A, we know that B is going to be the permeability of free space times the current all over 2 pi r. So this right here, we can just plug in what we know. We have 4 pi times 10 to the negative 7th times 2 amps all over 2 pi times the radius. Now the radius here, if you picture the loop here, the radius here is just going to be the distance between the wires. So that's going to be 0.001. Now if you crunch those numbers, and realize here, this is actually kind of nice because the 4 pi and the 2 pi, 4 pi divided by 2 pi is just 2. It's going to be 4 over 0.001 times 10 to the negative 7th. So working that out, I'm getting 0.0004, or you could say 0.4 milliteslas. So this is actually, the book gives this example because it's a wire normally has about 1 amp, and you might be wondering, some people say, like, what is the effects of the magnetic fields? We have so many of these fields running through us. Do we have any health effects? And so the answer is, if you go 1 millimeter close to a normal wire in your house, if you get that close, you'll feel about 0.4 milliteslas, which is weaker than the the magnetic force of the world. So the force of magnetism is actually incredibly small from just simple appliances. So the second question is, what will be the force of B? And so remember, the force of B is going to be and at this point I forgot to specify something, because looking at this, we have currents and we have the magnetic force, but what about the length? Let's just say that what is the force of B, and then we're just going to say on 1 meter of wire. So we're specifying it down to just looking at only 1 meter. Okay, the current is 2, the length is 1, and we know the strength is 0.0004. Working that out, we get 0.0008 newtons. Really, really small effect. So for you to see wires kind of naturally attract each other from the current, you're going to have to either increase the magnetic field, or you're going to have to really, basically in this example, really increase the current. So last thing here, we also have to look at the magnetic field created from loops. And so let's say you have a loop of current like this. Well, you're going to have actually, let's say the current is going around this way. You're going to have a magnetic field lines kind of coming out like this. Now the problem with this situation is that in loops, it's actually going to be kind of lopsided. It's not going to be perfect circles. And you're going to have also this, in the very center of the loop, a magnetic field just going straight through. So you can derive it, but I find that we really don't have to spend that time here. Just know that for a loop, and this is the magnetic field in the very center of that loop, it has a slightly different equation. It's 2 over r, and this is the radius of the loop. Okay, now like for solenoids, if you have many loops and you have them consecutively like this, you're still able to figure out that magnetic field right in the center, and it's a little different still. It's n, the number of loops, times permeability of free space times the current all over the length. So what I want to do now is I want to do an example of the electromagnet that we did in class. Okay, so for our electromagnet, we had a number of coils of 42. So we wrapped the copper wire around our nail 42 times. The length, when I measured out that coil, was almost exactly about 7 centimeters. And then the current, now I'm kind of estimating here, it's hard to tell exactly the current that was coming out of that 6-volt battery. I've tried to look online a lot of different places. The answer is really complex, and I don't want to blow another fuse on my multimeter, so we're going to estimate, and I think this is pretty correct. It's about a little less than 1 amp. It could be more because there's not much resistance, but let's just assume that that's the amount of amps. Okay, so to figure this out, number of loops or coils times the permeability of free space, which is 4 pi times, is it 10 to the 7th? 10 to the negative 7th. Times the current, 0.75, all divided by the length, and the length is 0.07. Okay, and when I plug this all in my calculator, I'm getting something about 0.00057.